Okay, Peter, you can start. I hope everybody can hear you.
Yeah. Hello, everybody, and thank you again. A long time since January when I visited Tel Aviv. I got really nice feedback from you. Thank you very much. And the main point in the feedback was I was pushing too fast to explain what relation division really is and what kind of problems it solves. Because as Jerry told us now, I was only given 45 minutes. So I have another presentation here now which explains more in detail what division is and how the queries have evolved over time to deal with this problem. And I will show you how queries have evolved from kilosized set to megasized sets and beyond gigasized and petabyte set. Okay? Let's shift to the presentation here. This is just about me. It's not to intimidate you. It's just to tell you I know a lot of stuff. So you can trust me on some things, right? Let's start with the theory of SQL Server and T-SQL language. It started with Dr. Todd, who worked for IBM at the moment, and in '73 he invented the SQL language. When he died, and Chris Date has continued his journey into the SQL language and how the language should evolve. And one of the pillar stones of relational division is actually relational algebra. And since database is a set, we are working with sets, so you can actually use the relational algebra to express what we're going to do with the data. And these 12 mathematical expressions are the main expressions we use. And what we're going to use the most in this presentation is the projection and the selection phase. Can everyone hear me? So if you have questions, just shout out, and I think Gary and I will handle them, okay?
Okay, if will be a question, I will let you know as soon as possible.
Yeah, great. So, as I told you, this presentation will focus more on what relational division is and how to solve certain problems, and also go into my implementation of how to be as fast as possible for petabyte sets, the gigabyte size sets. So what is relational division then? Well, you can ask questions like your boss giving you an assignment says, find me all customers who have bought product ABC and XYZ on the same receipt. That's a typical use case for this relation division. Or if you're having a dating site, you can say, give me all females who are blonde and have kids, for example. You have multiple criteria, multiple filters on the set, right? And for this to work, each tuple, each row should have at least 2 columns. In practical, there should be at least 3 columns. There should be one for projecting the result, the name, and there should be one or more columns for filtering the data, for example, age or gender. But when it boils down to core minimum, the simplest level of a relation division is actually a simple where clause. And I'm going to tell you and show you why a where clause actually is a relation division, but you don't think about it. So what is a division? Well, this is a normal arithmetic division, right? You take 11, you want to divide it by 4, you get 2 with a remainder of 3, right? So division introduces a concept named partitioning. You want to partition 11 in a bucket with bucket size of 4. How many buckets are you going to have? Well, in this case 2, and the third bucket is 3/4 full. The reason we don't use the reminder is because SQL Server uses integer division, so we're only interested in the two part. So, and the division is used over and over in mathematical terms, not only arithmetic. We can use polynomial division as well. We have a dividend, we have a divisor, we have the quotient, and we actually have the remainder. And this just goes on and on and on, even for matrix division notation, right? So, what then is relation division explained? How can we tell what it is? Well, Todd explained this very scholarly. He said that division is a binary operation that is written R divided by S. So the result consists of the restrictions of tuples. Well, you can read the text for yourself, but the problem is here that it's very difficult to understand. What's the question? No? Well, this is very difficult to understand with the tuples and restrictions and so on and so on. So let me be a little more less formal about it. So you can actually express the division in arithmetic in set-based operations, and this looks like this. And there are actually only 3 steps in a relation division. You want to compute all possible attribute pairings, you remove the existing pairings, and you remove the non-answers. And this definition has been very, very widely known, and the most common algorithms to deal with relation division is based on this expression. But it also involves a very big problem, and that is that you have double negations, right? Let's go back again, because you want to remove the removed ones. So the double negations is the most, this algorithm is the most prominent one. This is most common used before I dealt with relation division. And you can explain it like John Wayne says, there ain't no planes in this hangar I can't fly. Instead of, I can't fly whatever plane you want me to. It's exactly the same result, but it's expressed in a totally different manner because you use double negations. And for humans, double negations is very difficult to understand, and so is for the computer as well, because you want to remove something that is not there. Let's see an example. I have used throughout this presentation examples of Joe Celko's, his hangars and pilot skills table. You can Google them and see how they look like. I've just animated them. Let's see, we have 5 pilots. We have Celko, Higgins, Jones, Smith, and Wilson pilot. We have a table denoted in the gray area, all pilot skills. So we can see that the red pilot, Higgins, he can fly the Piper Cube, the F-14 fighter, and a B-52 bomber plane. Celko can only fly the Piper Cub, whilst Wilson, the orange pilot, he can fly 4 different types of planes. And all this is set in the pilot skills table, and we have a hangar table that says, find me all pilots that can fly both B-52 bomber and B-1 bomber and F-14 fighter plane. And we can easily check this visually by saying, well, this result is Smith. He's the only one that can fly these 3 planes and nothing more. This is called relation division with no reminder, because there are no reminder part in this set-based division. We can say, if you want a reminder, it looks like this. Find me all pilots that can fly the B-52 bomber, the B1 bomber or F-14 fighter or more. We don't care about their extended skills. We want to see this is their minimum flying skills. And as you can see, in this part, we actually have two pilots that fulfill our request. The Smith pilot and the Wilson pilot. Any questions this far? Okay, let's continue then. So by extending this logic, we can say I want to see which pilots are available to fly the Piper Cub plane. And you can write a T-SQL statement that looks like this. And this will give you exactly the same result. Celko and Higgins are available to fly at least the Piper Cub plane. So you're actually using division when you introduce a where clause in your set. Can you hear me? Because I can't hear anything right now.
I can hear you. I hope everybody can hear. I try to connect from another computer, so I guess everything is okay.
Yeah, okay. Let's continue. Let's make sure that everyone are on par with this definition that a where clause is actually a division, because you divide the pilot skills and sets. Give me all rows or pilots that have a plane name named Piper Cub in the skill sets. Right. This is one example to demonstrate relation division, and I can show, as I did in January when I was on site, where in the world is Isabel, right? I want to find all families that has a child named Isabel. To the left, we have a table in your database. It's a second normal form. It has three columns: the family name, the first name, and the age. And this is typically a T-SQL query you write to find out. Select the family name from families table where first name equals Isabel. And you actually get a result that says the Larsson family and the Smirnov family do have a child named Isabel. Right? Let's extend that one. We want select all families that have a child named Isabel and an age of 7. In this case, Larsson gets through, but Smirnov fails because both where clauses is not true. The problem with this one is it's only operating at one line at a time. And as you can see here, if I want to query my families that says which family do have a child named Isabel and a child named Samuel, the first query here will fail, as is so perfectly explained to me in the presentation I did at you in January, that says the first name can't change while we're querying data. So we will never get any result with the first query. And the second query, yes, we will get a result, but it's not the result that we want, because it gives us all families that has either Isabel or Samuel, or eventually both. But we want to make sure that we only want the families that have both Isabel and Samuel. And this is how we can write it nowadays with SQL Server, with the intersect operator. The problem with this case is that it covers the tables twice. You have to scan or seek the families tables many times, and if you have many criteria, as Isabel of age 7 and Samuel of age 5, and or a lot of more filters, you would have to write this query dynamic, because you don't know on beforehand how many intersects you want to use. So you want to have dynamic SQL, and that's something we don't want to use SQL Server normally. And how does this look when in a SQL Server? Well, Larsson family actually have Isabel and Samuel, and Smirnov fails short again because they only have Isabel and no Samuel. And actually this intersect query is one of the fastest. I've spent about 6 years developing this query, and during this investigation I have seen a lot of implementations of the relational division definition, like this one, ABR, pi, IAB, PPR. I always said that one, right? Because I've seen over 100 implementations, everyone different. The problem is that all implementation ever seen from the theory, and they don't derive from how SQL Server actually works when working with sets. In theory, you can define anything because you don't have to measure it. But when you store in SQL Server, you actually have to measure it, and then performance matters. I've seen over 100 implementations of algorithms doing this. I'm only going to show you about 10 at this time, because these are the 10 fastest I've found during these 6 years I've spent on this. First one is Celko number 1. As I call Celko number 1 because it's the first one I found. What he's doing is selecting from the pilot skills table, cross-joining with hanger table, filter out where plain types are equal to each other, group by pilot name, counting the result for each pilot name, and says that, well, the count should be exactly the number of planes we want in the hanger. Is this clear? Do you understand the logic of this query? Yeah, it's quite straightforward, but it isn't that fast as we're going to show you later, right? This query is also made popular by Chris Date, and he uses it over and over again. And it is fast on small tables like kilosized, 1,000 rows, or perhaps a few thousand rows. But when it comes to million row sets, megasized, or even gigasized with billions of rows, it will fall short immensely. And this is another query that Celko has written. He has quite an imagination how to deal with the theory of relational division. What you do here is you say that I want from hanger these 3 plain types. Get me all of this one, and remove the ones that I can see that the pilot skills are already have the certification for. Okay, now we have a set that is an inner and outer bound, and this set should evaluate on every row, outer row in the pilot skills. It says select everything from pilot skills where I don't get a hit of the ones I want minus the one I can see. Well, as you can see, they are not easy to understand, but they work because they are a straightforward compilation and translation of the theory, and they work. Then we have the most popular one, the Todd's division. It also handles with only no reminder. It can't handle if there are reminders in the set. And actually this query is written by Pierre Moulin and very hard advocated by Celko, right? Now we're getting it 3 levels deep, and it's very, very advanced to understand. If I were to put this code into production and give it to a junior DBA, I doubt they will ever understand it, because it says, do me the Cartesian product of pilot scales and hanger, the cross join. Select the distinct set of that one where I don't have a match on pilot scales, and the pilot skills are not found in the hangar. And this is a double negation again. Give me all planes. There are no planes in this hangar, I can't fly. This is what it means. The problem is the not in, where not exist, and not in takes very, very long time for SQL Server. And now we get in Celko has also evolved, and he wrote this kind of query with the left join. The upper one is Celko original, and the lower one is rewritten by me to actually change the query to allow the reminders. As you can see, the only difference is the count of ps.planetype is equal to, in the original one, and to accommodate for reminders greater than or equal to with my rewrite. So we can actually use them in both cases. And then Celko wander off, because now in SQL Server 2005 we had partition functions, and we see how imaginative he is to use them in Relational Division. And this is just another example to facilitate the theory with different kind of queries. Here is, for example, Celko number 4. We had used the partition aggregated window functions over partition by and so on to get a result, but I can tell you they are not fast. And this is actually the fastest one that I call Celko number 5. So let's see how they compare on very small sets, like in kilosized set, as a few thousand rows, 100,000 rows, and so on. You can see a difference here. The SVPS query is my query, the one I'm going to explain to you in detail why it works very well, and all the other ones are the fastest ones of the existing one, and Celko is the most prominent one. And there's a quite of performance difference here. And this is only the number of scans and number of reads for this small set, a kilosized set. There is a SVPS experimental there. I experimented with another kind of set with binary values, and it was very, very fast. But it's kind of cheating, so I'm not using it. And this is when you allow for with reminders. As you see, when you have no reminders, a comparison chart, the queries are not that different. They perform somewhat equal. But if you allow for reminders, if you only give me all pilots can fly plane type A, B, C, get me this one. Even if they can fly more planes, we don't care about that. We have a minimum of A, B, C. We have with reminder, and now the queries are getting more less performant. There's quite a difference. So this is Celko number 5 is the best performing for exact division and reminder division, and this is my rewrite. And this is only a number of reads and number of scans, but what does it say about timing? Well, for a kilosized set, the difference is not that much. So I've extended my tables with pilot skills into a few million rows. I think about 5 or 6 million rows, something. The difference is very, very profound. This is the time taken to do the reminder division. It took my query 39 seconds to finish, and Celko I just aborted after 5 hours because it was not finished yet, because he has this one kind of double negation, or he has this count of group by and count and stuff. So Celko's query was aborted after 5 hours, and my finish in 31 seconds. And this is number of reads until abortion. So when I got to this point in time, it was about 2012 or something. I was dumbfounded and thought that why isn't there an algorithm that can deal with both reminder division and with no reminder division, exact division? So I started out and wrote a few algorithms and tested them, and actually found one very good algorithm that is very, very fast for kilosized set and megasized set, a few millions of rows. And what I found out is that I do not want negations. They are very, very hard for humans to understand and equally hard for a machine to understand. And also I've noticed a few points that if I want a division, there's no need to ever to check for lesser number of rows for any pilot. Let's say I have a hanger that has 3 plane types. And if a pilot only has certification for 1 plane type, there's no need to ever include him in the result because he can never reach the number of sum of 3 certifications. And I also wanted my algorithm to facilitate both exact and reminder division. Right. So the easiest step to reach to this algorithm is to write this one. You join the pilot skill with the hanger on plane name because this is the plane name you're checking for certification, right? Well, this is not enough. This is obviously not enough because this only matches what we want, the hanger, what we are offered in the pilot skills. We want to see if each pilot can match at least X or any number of certifications. So we add actually a cross join in this case, and I'm going to see later why it does that. So we have an inner join between pilot skills, what the pilot skills we offered, and we inner join that on hanger, the skills and the plane types we are demanding to have a match. And checking the number of rows in hanger, we can see that we are looking for, in this case, 3 plane types. If the number of counter hanger is 3, right? So we add another inner join to pilot skills again that says for each pilot, count up the number of pilot skills or certification he has earned and check that against the number of certifications that we want to check for, the number of rows in hanger. And you do it like this. And here we can easily filter out the pilots that does not have the minimum number of certification that you want. And you can easily get rid of half the table if you have, let's say the hanger is 5 plane types or 5 attributes we want in the dating table, which should be blonde, no kids, car, have her own apartment, and so on and so on. So the more specified you get with the query, it actually gets faster and faster, and not more complex. It actually gets faster and faster because more and more pilots are omitted because they don't reach the number of wanted certifications. So we can change exchange the greater and equal to exactly equal to have exact division, or we say that greater than equal to, we want at least this one. If I have more certification, I don't care, right? And now we tie this together. That says select the PS1 pilot name from the PS1 table, the pilot skills. We inner join them on hanger that says I want all pilot skills that has at least this number of certifications, joining out to pilot skills again on pilot name, and inner join a hanger again on plane name or plane type. That says the count of hits for each pilot should be the number of hits in the join. And this, I've tested this over and over again. It works very, very well for a few thousand rows up to 5-10 million rows. It's very, very fast and very, very versatile. And there it is. This is what I find out. And if you want to learn more in detail, you can buy this SQL Server Deep Dive 2 book. We don't get paid for it because we donate all our royalties to Operation Smile, which operates on cleft palates and children all through the world. They also can extend it if you have multiple hangers. We have a green and blue and red hangers. We can do 3 divisions in one step. Just add a hanger ID to the set. And I thought I was content with this solution because it's versatile, it works with any kind of use case, until I got a customer in 2013. They were planning to have a gigasized 1 billion rows in the table. And the current implementation said that, okay, they had a solution that says, well, if you're going to use this one, it's going to take 134 days to run the query. And that was not good enough because of an SLA of 20 seconds. So naturally, we added 1 billion rows and tested my unified algorithm and found out, to my horror, it was too slow. It didn't even get under 20-second SLA limit. And I was questioning myself, why is this happening? Why is this not working for a gigasized set with millions or a few billions of rows? Well, it has to do with the limitation of SQL Server. So the first thing you have to understand why this query is not working for very large sets is the logical query processing order. I'm going to discuss that, what that is. The problem with this query is SQL Server is free to rearrange the tables for you in another order if it thinks it has a better result. And the way it decides which order the table should be joined is ultimately based on the statistics on the tables. The problem with statistics is you have only 300 measure points no matter how big the table is. So if you have 1,000 rows, statistics build on 300 measure points, every three row, that's okay, it's good enough. If you have 1,000,000 rows, well, you still only have 300 sample rows to build the statistics on. Things are going to get very, very skewed. And when you reach a gigasized set with billions of rows, the statistics for SQL Server is no use to you. It makes all kind of different assumptions for you that is not true and will not help you at all. Then I dived into this logical query processing order to see what is SQL Server doing under the hood while calculating the result I want. I turned to a fellow Israeli of you, Itzhak Ben-Gan. I have his permission to view his poster, the logical query processing order for you. What SQL Server does when you have a from and join and join and join, it does this in an iterative step because it starts with one table in a from clause, takes that into memory, and then do a next iteration, well, and do an inner join. The inner join, what it does internally a cross join, and then afterwards apply the filter, the on clause filter for you. Then I realized, well, SQL Server is not doing my unified algorithm in all at once operation. It actually does in an iterative process. And this is a eureka moment for me. It says, okay, if SQL Server is doing iterative phase, so can I. We're not going to discuss further this other where class and group by because it happens later, right? And the base of the root of all your bad performance in my unified algorithm is the SQL Server Statistics. Many of you have seen this. It says DBCC show statistics. For a table or index, you get a result that is similar to the screen, right? You have the object name, you have the density, and you have the key values, the ranges for each key. And here is where you have the 300 measure points. It says that right from 0 to 1, we have 0 rows. From 1 to 1064 as the high key value, we have 1062 rows. Between 1064 to 11,478, we have only 127 rows, and so on and so forth. The SQL Server has a very detailed statistics of how the keys are used. The problem is there's not enough samples. There's only maximum 300 points only. So at this moment, I just thought to myself, because I was sitting at this client and my algorithm didn't work, well, how can I change my algorithm to deal with gigasized sets and ultimately petabyte sets, 1,000 of billions rows? I concluded that I want to have better statistics that SQL Server can provide for me. So I was told about that. And I want to have better control of data access and better control of which order tables are joined, because I don't want them to be random. I want to have complete control of what I'm looking for at any given moment. And also want to have access if there's a seek or a scan. And also want to have separate selection from projection phase. So these 4 design ideas were the core improvements. In order to do this, I have to write a completely new hybrid data model schema for this EOV table. Right? We have the dim entity that it says these are all the objects we are using. We have a dim entity type that says what kind of object is the entity. It is a lease contract, or is it a medical journal, or whatever we want. This is the entity type. And then we have this EOV table where all the raw data is stored. And also we have an extension of the normal EOV table that says we have the dim pair table and we have the dim attribute. The attribute table, the dim attribute table, is only a naming convention for what kind of data we're dealing with. Like, this is a SSN attribute, this is a street name attribute, this is a city name attribute, and so on. What I concluded is I want to have a dim pair table, because I want to say that if this date of January 1st, 2015, that in Sweden is denoted 2015-0101, I want to know that this actually is a date and nothing else, like a salary or something. So with my dim pair table, I keep together both the code, the value for the attribute, and name them as a dim pair, and the pair together gets a unique identifier, the pair ID. And then I store the pair ID into the fact EOV table, together with redundant information such as entity type, because I also have the entity object in in fact AOV, so I can actually get the entity type if I want to by joining entity to fact AOV and then joining to fact entity type. But it turned out this redundant information actually made the queries about 20 times faster, because in many cases we don't know what we're looking for. We only know that I want all documents that has been signed by a doctor. And the doctor is an attribute, right? But if you talk about I want all documents that is signed by Dr. Smith, that's a pair. So you can change the scope of precision for your queries when dealing with relational division, and that's why I have that looks like the redundant information in fact AOV table. So we have the pair ID, we have the entity type ID, we have the entity ID, and we have status. The status column is interesting because it allows us to deal with multiple versions of a row, because we import the data, we can import it into fact AOV table directly, and all imported data but not checked or verified data gets status 0. And then when the controller has checked the data and sees that everything is fine, we can update the status to status number 1 that says this is checked and controlled, go ahead in production. So we can actually change in the when we search for the data that says I want only to see production class data with status number 1, or if the controller or management want to see all data, even the data that is imported but not checked with status 0 or status 1, that is translated to greater than or equal to 0. And these are the tables used for the hybrid data model schema. And I'm going to start with the statistics snapshot table, because we are actually running our own statistics much in a similar way as SQL Server is. But we have actually a trigger over the fact AOV table that when you import data in the fact AOV table, it aggregates and maintains the fact statistics snapshot table for us automatically, so we don't have to care about that. So how does the fact statistics snapshot table look like? Because this is the key point of performance. This is one example how statistics snapshot table looks like. We have for each and one unique pair ID, together with the attribute and the entity type and the status, says I have exactly one row in the billion row table that has this setup. Or for pair ID 32,895, for attribute 8, we have 25 rows in the billion row table. And this is very, very high precision, because I said every permutation we have of pair of attribute and entity type and status, I know exactly how many rows we have in the billion row table or more. And this makes it easy for us to decide what I showed you earlier. The problem is problem of which order should the tables be joined, because now I can start very much in a similar way that SQL Server does in a logical query processing order, with an iterative phase of building up the joins. I can actually start with the pair that is the most unique one. I know I only have one row in the total table of pair ID 193.193.02. I can start with that one, because all I write to the store procedure is the AND clause. I want child name Isabel and a child named Samuel, or I want pilot scale of B14 fighter, F14 fighter, or B52 bomber, and something else. So whatever you're doing in relational division, there's an AND factor, an AND clause to it, right? But the AND clause is operating on multiple rows. So for each iteration that says, give me all pilots that has F14 certifications, and I can see in the statistics snapshot table that is, hey, I have only one row in complete table. I start with that one, because then I can see the B52 bomber and B1 bomber. I have 25 pilots each of those one. Why not start with the one only, and then in or join in an iterative phase with the 25, and the result could be only 1 or 0, because we have an AND condition to each iteration. And going from the least, the most unique one with the least number of items, joining into a bigger one, makes SQL Server using a seek, or actually if the 25 should be 25,000, it actually builds a hash table for us, doing an inner hash join in the correct order. So why can I tell you that this is very, very fast? Because we can do clustered index math on this one. I did this one when we only had 1 billion rows in the table. 1 billion rows in the table with this setup uses 2.2 million pages in the leaf level, in the clustered index, right? The intermediate levels is that for these 2.2 million rows, 2.2 million pages, we need 4.7K, 4,702 pages to control those. Then we introduced another intermediate level that says for these 4,722 pages, we need 10 pages to control them, and we always need a root level of 1 page that says 1 page. So we actually have 4 levels only of the clustered index, only, even if you have 1 million rows in EOV tables that says 1 billion tags. So the clustered index is very efficient because the key size is only 9 bytes. And how is this possible? Because Copenhagen or Tel Aviv or other city names, they are like 20 characters something. But since I have this pair table, you have DPI code, that is Warsaw data. But this gets translated into a 4-byte integer. And this is also the key to have wildcard searches in my model translated into equijoins. Because if you want to search all cities that starts with LON, you only have to scan the dim pair table for that attribute. So you only do a partial scan of the dim pair that says, give me all cities that start with LON, and for each hit I get the corresponding pair ID out. And then I use that pair ID to do an equijoin to fact EOV table. So no matter what I search for, ranges, wildcards, I get an equijoin on the fact EOV table. And for this customer, now I have a design idea how to write things. So I showed my customer in one meeting. It says, for now, when you have 100 million rows, only 100 million tags, it takes this time because the clustered index level is only 3 levels deep. And when you exceed 47 billion rows, your clustered index is going to change and reorganize itself as 4 levels deep. Sorry, up to 47 billion rows, you have 4 levels deep, and when you exceed 47 billion rows, the clustered index is going to have 5 levels deep, but then it can accommodate 22 trillion rows and still have the same performance, because when you're doing a seek, you are only traversing the clustered index 3. So if you have 4 levels, you'd only have 4 I/O to get 1 row out, no matter how many rows there are, until it exceeds the 47 billions. Then you can have 5 I/O to get the first starting row out. And the next design point was the fact EOV table is clustered on the pair ID, the combination of the value and the attribute. The pair is the clustered key in the fact EOV table. Because when you do that, you can get an operation that in name SQL Server, the clustered index seek and ordered partial scan. Because we have all the pairs stored sequentially in the pair ID order that says, I want to search for pair 11. Then all 11s are stored sequentially in the leaf node of clustered index, and SQL Server is then smart enough to realize, okay, I can start with a seek to the page, and when I reach that page, I can continue to scan part of the leaf nodes when the 11 finishes. And if there are only 25 rows, they are contained within one page, so you only get 3 I/O to get all the 11 rows out. Or if you want to search for, I want all customers in London, and you have like 100,000 customers, you get 3 I/O to the first pair ID that matches City of London, and then you scan the very few pages to get all the City of Copenhagen or City of London with your result. So you don't touch, you only touch those rows you actually are interested in. And this is possible because an efficient clustered index is what you should call news, right? The N stands for narrow. You want to be the clustered key as narrow as possible, and in our case, it's only 9 bytes. You want to be as unique as possible. Well, they are, because the pair ID together with the entity is unique. You also want this SQL Server to have a clustered index to be static, ideally never updated. And since it is the key, you have only translated the data into a pair ID, it never will be updated, right? And you also have the E part of the clustered index that says it should be ever increasing. And it is, because every new type of pair, if it gets a new, if the fact EOV table or attribute table gets a new value that has never been in database before, it gets a new identity value of the pair ID, which is at the end of the deemed pair table, and therefore it's also inserted at the end of the fact EOV table. And the only trade-off I've seen this far is when you have the clustered index insert. If you have a huge import with very old values, like age 47 or something, that is a pair 81, you will actually have to rearrange all these billion rows, because the clustered index says here is pair 81, so we actually have to physically sort them on disk. And that's the only trade-off. But then you have to know your data, because if this document system, you mostly just insert the data once and you can read them over and over and over again. You rarely change the data or delete the data.
Excuse me, Peter, we have a question of Itai. He says that you mentioned only clustered indexes and not non-clustered indexes, and he asks if it is by chance or this is your intention.
This is my intention, because I want the clustered index seek and order partial scan to happen, because I differentiate. I want, my first phase to get all the entities out I'm interested in, and when I have the interested, I then use a secondary non-clustered index to get all other attributes or attribute values out of the database. The problem with my unified algorithm that I had before is that I did both the projection and the filtering phase at once. And what I'm doing now is I separate the filtering phase from the projection phase. And for the filtering phase, I'm using the clustered index. And when I have all the entities that fulfill all requirements, I go back to non-clustered index and get all other attributes out that I want, and that's the projection phase. Is that an answer you wanted?
Well, on behalf of him, I hope it did. If there are more questions, you can always use the option, the question options that you can find easily in the right part of your screen. Okay, you can continue.
Okay, I just minimize that. Okay, right. Well, because this customer, the data was imported once, and for legal reason, the data should stay in the database for at least 10 years, and that equates to about 15 million reads during the 10-year lifespan, right? So how can we make this more intelligent? We know how to design things, because we have better statistics and we now have better control of the data access method. So how can we make it even more intelligent? Well, we can control the order of joins because we're using the new statistics snapshot table that says start in an iterative phase with the most unique attribute we're looking for. So this is just a schematic of how the first phase is built. And actually this is the most important one, because the total procedure is about 650 or 700 rows or something. So it's a quite big procedure of 650 to 700 rows code. But the pre-execution phase of the SQL procedure I'm going to show you is 550 rows only to optimize the solution. And one of these optimization is to control the order of joins, and we're doing that by controlling which attribute should I start with, the most unique one, the second most unique one, and so on and so on. So what we're doing in the store procedure, we unpack the facts, we check the heuristics or the statistics snapshots, and we iterate the facts. And we then get every entity within the fact, and if it's a multi-valued, like a wildcard or something, we just iterate that attribute until we get to the end of all attributes is done, and then we're finished. We're going to show you a little bit of that in the store procedure, right? And within these 550 rows of code, we have a direct short circuit logic. This says, if you want to search for, get me all applicants that lives in the city of New York or New Delhi, and that is level 3 approved, yes. I want all these rows, all these applicants out of my applicant database. But I don't want the consultants that are self-employed, or consultants that lives in a city that starts with new. And as you can see, the negative search attributes directly invalidate the positive search attribute for city, because both New York and New Delhi starts with new. That says, and like the code the procedure say that, okay, the negative search parameter city invalidates all the possible values for city for the positive, and therefore, since New York and New Delhi is invalidated, no matter what I do with the rest of attributes, I will never ever give a result anyway, because there is an AND condition. Because you wanted all applicants for New York or New Delhi together with level 3 approved. There's an AND operator there, and if one of them is never true, the complete statement is never true, and if we can calculate this before, we will never ever have to even touch the billion row table. Do you agree? So if we can calculate that the arguments that we send to the database is a direct short circuit, we will ever have to even touch the full billion rows, and we will not even do a join at all, because we know the full statement can never be true anyway. I'm also checking for indirect short circuit logic. In this case, I wanted to have all applicants of New York, New Delhi, or London, and they should also be approved, all the applicants. But I don't want self-employed ones and those one who lives in cities that start with new. In this case, I only invalidate New York and New Delhi, so the question sent to the database is refined as I want all applicants that lives in London and are approved. So we actually save 67% of the performance because we only have to search for one city and not 3 cities. And but we don't know if it's going to give us result anyway, because we have reduced the number of scans or seeking for effective table as much as possible. So I have a number of mechanisms in my procedure to check for this one. And this is what I call the structured data control. It's 18 rows. And this is taken from one of my examples that I'm going to show you at the end of this presentation. I have 8 demos that are going to seek from the database, search from the database that you can see on a billion row table is going to be very, very fast. In this case, I have an attribute of 10. You can see there are 15 rows. That is actually a wildcard search, because that is the attribute of SSN, Social Security Number. And in Sweden, Social Security numbers are made up by the year, the month, and the date in total ISO format that says 1953 04 25. That he's born on 25th of April 1953. Right. So what I sent to this procedure was a wildcard. I want all patients that was born on the 25th of April 1953, and what SQL Server find out without even having to touch the full table yet, the fact EV table, only touching the deemed pair table, it says, well, I have 15 matches for you. And these are the pairs, the pair ID. So this wildcard is translated into an in case. I want this or this one or this one or this one. This is multi-valued for that. I want this SSN where any of these is true. And this is a perfect example of how I can translate a wildcard or a range into equijoin, because now we have exactly all pairs for all these patients that are born on 25th of April 1953. And then we have 2 rows of attribute ID 12, and that is also a multi-valued, because that is probably, we're going to see that later in a demo, that is probably the hospital. I want hospital downtown or the hospital of airport. I don't know, something this, right? And then I also have a negative search parameter. You can see the column is positive. There is there was two negative for the 12 attributes. That is probably I don't want records from these departments. And then I have a second positive attribute of attribute ID 2 that says something. And now I also get from the fact statistics snapshot the items that for this pair and for this entity type, I know exactly there is 1, 1, 1, 1. There's 2 rows, 106,000 rows, 35,000 rows. So why would I want to start to fetching 37,000 rows out of the database when I know the next iteration will only give me at most 2 items? It's much more efficient to start with the list number 1 that says give me this or this one or this one, because I know it only will have 2 medical journals at most for me. And then in the next iteration phase, use those 2 rows and joining them to 37,000. It's much more efficient. So what I'm going to show you now, I was not sure about the timing here. I'm going to show you the first 550 lines of code. And those 550 lines of the total of 650 or 700 rows something, they are just for validated input, changing wildcards and ranges into equijoins, and checking short circuit logic. Let's see if this works. Yeah, I'm recording my screen here just to see how much code there is to check all these things for the pre-execution phase. To see if do I even have to touch the full table anyway. And if you go to my website of secretopia.com, you can actually download all this code if you want to have more in detail to see what is this statement doing. I put comments there and everything out. It's quite self-explanatory. You can download the code, and you can also download the schema from my secretopia.com site. Just go to presentations, and I think it's Tel Aviv or another city I've shown this as download the EOV code, and you will get both the store procedures, the code, and the schema. Right. And that's 550 lines of code just to check what do I want to seek for and with which order. Right. And now we're going to get into the next 150 lines of code. And this is actually the filtering phase. This next 150 lines of codes is just for getting the data in I want, right? Let's see if that works. Okay. I have it here. See. I can just do it once more, explanation, what's going on. Here I start at line 553 that said, truncate my multi-choice table. No matter if there actually is a multi-choice or not, I'm going to use this table, right? And then I'm going to select top 1. What is the next attribute I'm going to work with? And that's decided before with the 550 lines of code, 1, 2, 3, 4, 5. In this order, I'm going to search for the pairs. And then I have an optimization that says, if this is the second or more iteration, and I want to search for an exact pair, do the statement that is on line 580. Or if it's the second or more iteration, and I don't know the pair, because I want to search for a document for a doctor. I don't know which doctor, and just a doctor in general. The code in 595 will be executed because it has an additional join to the dim pair to get the attribute out, right? And then I have two more statements that says exactly the same thing. If it is the first iteration, just put the data into multi-choice directly, right? And when I have iterated all multi-choices, in this case there were 15 rows, because I wanted a wildcard that says give me all the persons that were born on 25th of April 1953. I get 15 iterations here, and they're very, very fast. And when all the multi-choice is selected, I start here that says, is there something already that should be omitted? Like the negative. I don't want the data from department F or department G. I want to remove sets. I do it already here between lines 635 and 660. That says I want to remove these because I don't want these pairs to show up in the end result anyway. And this is also optimization, because I know for each iteration there can only be as number of rows as there was in the previous iteration. So I want to remove as many choices I have in an earlier step as possible. And the last step of this 150 lines of code is just that merged entity with the rows remaining in the multi-choice. And it says if I don't have a hit, add it. And that is only going to happen with the first iteration, right? But if I do have rows that is not, if I have rows in the source, the entity, sorry, if I do have rows in the entity for the previous iteration that is not present in the current iteration, when not matched is going to happen, delete all rows from all previous iteration that has no hit in the current iteration. So I remove them as quickly as possible. And then I have a short circuit and prematurely that says, well, if I'm still in an iteration phase between all the attributes, that says, is there at least one entity left? Continue with next iteration. Because this is important, because what if I search for 7 attributes or 7 attribute values, and I know already from the second iteration that we have no more hits. There is no entity in the complete 1 billion row table that fulfills iteration 1 and iteration 2. There is no need to continue with the next 5 iterations. There's no need, because it's an AND condition and it has already failed. So we have a prematurely existing here in 676 that says, if there's no more entities left after this iteration, stop here. And then we do a cleanup, and then we do select the entity from our result. And this is doing only the filtering phase, because this sends back to the client a list of entities that has fulfilled all attributes that we're looking for. And in general, all these 700 lines of code generates about 70 queries. From splitting the facts to checking all this short-circuit logic and everything else, it's about 70 queries in general. And it actually finishes in 40 or 50 milliseconds, even if there is 1 billion rows. And I'm going to do the demonstration again that I did in Tel Aviv. I did it very, very quickly then because I didn't have the time. And if you're interested in helping me convincing Microsoft that having a built-in operator or for a relation division, just go into Microsoft Connect and upvote it. That says this is useful. There are many use cases for this one. Not only dating sites or finding out the receipts. There are literally hundreds or even thousands of use cases that could benefit from a relation division operator like merge. So if we go in here, there is the long URL, connect.microsoft.com, SQL Server feedback details 670531, move T-SQL language closer to completion with a divide by operator. Or you can use the shortcut bit.ly U321HC. Go in there, upvote it. You can see I put also examples of algorithm for Microsoft to figure out that, well, this is necessary, right? And what I'm going to show now is my demonstration. I'm going to shift to Management Studio. Gary, can you see my Management Studio now?
Yes, we see the Management Studio. It's okay.
Yeah. So I'm going to run here now. This is 8 demos. They're going to get more and more advanced. And now, since I have explained to you what the procedure does and what it checks for, it might be easier for you to understand the demos as well. So what I'm going to do here is to see the sheer amount of data. I am actually working with a table that has over 1 billion rows. So you can see that I'm not cheating. It's not stored in memory. It's not stored in data cache. And as you can see here, I have only 10 gigabytes devoted to SQL Server. There's 1 billion rows. And the query took 33 seconds just to scan the full clustered index. Took 33 seconds. So you can see it's huge, a very huge table of 1 billion rows. So let's see what we can do here. Let's do the first demo here. It says we have first the filtering phase, right? Get me all documents, insert. I want all documents for this person that is born on 26th of June 1924, and this is just his full social security number, and is for entity type 1, that says I only want medical journals. I don't want his leases, I don't want his contracts, only want his medical journals. And this is only data that is set in, this is the status. I only want data that is actually set to production use. Then I take the time to do the filtering phase. What I'm doing later is I'm selecting from the table variable, cross-applying a function. The function by itself is very easy. You can see here what's it doing. It's using the entity ID and the entity type just to select all remaining rows in the fact ERV table that fulfills this entity ID, right? So here is the filtering phase. I'm timing that one. Then I'm doing the projection phase and timing the total time of both the filtering and the projection to get a timing out. Remember, I'm getting all documents for this specific person on 1 billion row table. As you can see, the filtering phase took 230 milliseconds. And just to count them to 33 seconds, 33,000 milliseconds. And in this case, entity number, we have one, we have two hits. We have one hit here for entity ID with all these attributes and all these attribute values and the status, and we get another entity out, this entity ID for the same person, and together both projection and filtering took 230 milliseconds. And this is done on my laptop. You have to remember that I have a spinning disk. It's a spinning ice chassis with 7,200 rotation per minute, and I have a 4-core laptop with 16 gigabytes of memory with 10 gigabytes dedicated to SQL Server. So this is actually 10 times faster on a production machine that my client have, because they have a really fast working sound with SSD disks. But this is a laptop, so you can have to count for that one. And this is when we search for exactly that person. We can, let's see here, if we can, go to next demo that says I want all documents for this person when he had this position in the company. Run that one. You see, from 230 milliseconds down to 30 milliseconds. And how many hits do we get? Only one entity. The entity that starts with 3 million something, right? And this is the power of controlling the iteration phase, because this is probably doing that. I started with the position code because I have about 14 or 15 documents for this exact person, but I have only one row in the complete the 1 billion row table that has this position code. So the more attributes you have, the faster the query, the procedure will actually get. 30 milliseconds to get this out. And I've done some mathematics up here. We don't care about the original model because I have rewritten the total. And you can see here, this 15 rows of data get out in total, 14 rows, 14 tags, divided by 1 billion total, gives us a search rate of 7.7 billion rows per second. And we actually scan 550 million documents per second. And each document have a varying range. There can be 2 attributes, there could be 2 tags, or 15 tags, or even 30 tags per document. But we scan 550 million documents per second. Let's continue with demo number 4. Here we have the wildcard search, right? I want all persons born on 26th of June 1924, no matter what the last 4 digits are, right? Doing the same thing. And we're back to 100 millisecond sampling. But we also get 16 documents back. 16 documents that has a person born on 26th of June 1924 on it. And now we have this that I had an example. We want to have a wildcard of all persons born this day, but give me all documents for these persons, but I don't want documents that consist of department G or F. one again. You see about 100, 180 milliseconds on a billion row table to fulfill both the positive search criteria and also the negative search criteria. And as I said before, we have 14 documents in total. Now we only have 11 because we wanted to remove the G or F departments. And it took like 100 milliseconds only to do this one. Let's do a little more advanced. Let's do, sorry. We want to combine a wildcard search for these persons born this date when they have had another position, not 1, 2, 3, but they have 1, 2, 2 position code. But we still don't want those documents made for department G and F. We still only want medical journals, but this time we also want all non-validated data. Run that one. What have we here? Ah, sorry, that should be. Like that. Yeah, now it's true. 150 milliseconds on my laptop. And now we got only 2 documents again that fulfill the request. All persons, that were 14 people. The position code I don't know, but we want to remove this one. We also want the non-validated data. And we can extend it further to even have it. And they are denoted with my implementation as colon. We want all documents that has a project start this month from the 1st of July 2012 to the last of December 2012, and the position code should be 122. I want all of those documents, but exclude the documents that are made for department A or B or L, and also exclude the documents for these persons that we have used before. Medical journals only, non-validated data. We're up to my laptop 300 milliseconds to do all these checks at once. And you can see we have 182 documents returning from the stored procedure. We have all documents that had a project start for these 6 months with a position code of 122, but I don't want them for these apartments or these persons. 182 documents back in 300 milliseconds and total of 500 milliseconds. Because the filtering phase in this case took 180 milliseconds. And and the last demo I have is actually this one, just to see that I'm not fooling around. I'm not having the data stored in hot cache. What I'm doing now, I'm actually going to drop the clean buffers. I'm going to drop the free pocket cache. This is exactly like starting the SQL Server over again with the reset button or cutting the cord and powering up from the beginning. But we're still doing a normal search. The most common search made in my client that said I want all medical journals for these persons on this day. For this position code, this is actually a medical treatment, but not for these departments. And we're doing this on newly started SQL Server, right? Because we drop in the clean buffers, we drop in the data cache, and we drop in the procedure cache. We'll run this one. And it takes a half a second to complete all these tasks. And that is actually all I have for this presentation. I don't know how long we have been running? 1.5 hours or something?
About we have already 1 hour and a half till now.
Yeah, okay. So I don't have more at this point. So if you have any questions, please ask them now, or if you want to find this interesting, please upvote it on the Connect, and also please download the schema and the code to play with and see if you can implement it into your applications.
We will wait half a minute to see if we have other questions. Anyway, all the presentation will be uploaded soon to the YouTube, so everybody can watch it again and show all the links that you have mentioned during it. And if you have additional materials that you want to share with the attendees, so well, please send me and I'll do that. As far as I see, we don't have
I can write here.
Okay. SQLtopia.com. Okay, I hope everybody can see it. We don't have more questions, and well, we have to thank you very much, Peter, for your contribution to our community. The second time you contribute so much for us, and
it's no problem. I hope things are getting a little more clearer now, and very fast paced than in January.
Of course. Well, thank you again, and hope to see you in the future in the next event.
Yes, I hope so too.
Well, see you, and thanks to all our attendees too.
Yes. Okay. Bye.
Bye bye.